So I was given the title Innovative Seismic Design as opposed to Performance Seismic Design. Perhaps that reflects some doubt as to whether innovation itself is desirable. We'll find out. This is my first picture, 1976. That's Helmut Krawwinkler and Carl Pister over there on the left. I think I actually took this picture, and then there's a picture of Ann Kiramijan, who looks the same today as she did back then. I don't understand that. And this picture you've seen several times. I just wanted to add, I'm the guy in the white suit, white coat there. This model, I made this model. This was made out of spring steel, so it would never yield. So perfect model for seismic engineering. We could see how a building would perform if it never reached a limit state. The really cool experiment I did was I put somebody had told me something about a tune mass damper. And so I took a little threaded rod and put some nuts on the end and tuned it by raising and lowering the nuts until I got it to exactly the building period. And we started it up. It lasted 5 seconds and then shot across the lab, proving without a doubt, because the building didn't move until after it was shot off across, proved that it worked. This is just a group I wanted to pay a little bit of, I think that's Russ. I'm pretty sure that's Piot there. I mean, it's been 50 years, but anyway. Piot took my place at the lab. I went out and went to work for somebody that was designing buildings. Helmut Krawwinkler, we've already been through all this stuff. I just wanted to mention that Piot followed me at the Bloom lab. I was out in the industry designing buildings. I came back in the late 80s and got a PhD, but I was under the Center for Integrated Facilities Engineering. And this is probably the first time I'll mention this, or last time I'll mention it. I was pushing high-def BIM as a way of implementing better engineering, okay? And Helmut was my advisor because Helmut, at heart, was a guy that really wanted to build buildings, design and build buildings. Helmut and I started a company in 1995 with Piot Moncars and also with John Ostras. John was similar to me. He followed me at the Bloom Center 1 year later, and then he came back in the late 80s and got a PhD. And the interesting thing, I went back and looked through all the PhD dissertations, and John's dissertation appeared to me to be an inflection point. Up until then, it was all model-based research, and after John, it started to be performance-based research based on analytics. This was 1990, so it was just when we were starting to have a computer revolution. A little bit later in time, when we started this company, Helmut said, well, we got to have a company that has a vision, and this was Helmut's vision. It's no longer reasonable to design structures based solely on the strength approaches contained in current codes. We must focus on performance-based design that considers all limit states relevant to the owner and society and pays tribute to life cycle cost. So that's where Helmut was in 1995. In 2006, I have to say that Helmut saw what it looked like making sausage and sold his shares back 3 years later and said, I'll just be a consultant from now on. A wise move on his part. In 2006, as a matter of fact, when Helmut got out, we were just starting the Grand California Hotel down in Anaheim. George Lucas looked at the hotel and said, I want the architect that did that hotel to do my school of cinema at USC. Well, okay, so the architect came in. The architect brought me along. I had to explain to the USC guys why a guy from Stanford should design their school of cinema. Fortunately, they approved me. So then I went back to Helmut and I said, Helmut, I'm going to design the school of cinema. What should I do? And Helmut said, design a building that can be repaired after a MCE. Oh, okay. Let me see, go through my code and see which one of those satisfies that requirement. None. Okay. Not only that, George Lucas wanted a building that was concrete or masonry, one or the other. because he wanted to have a Venetian stucco facade, and he would not settle for anything else. So we started out, we said, it's not going to be masonry, period. Don't even think about it. Maybe concrete, but we got to figure out a way to make it work. And Helmut and I spent a number of evenings at his dining room table with a bourbon talking about this. And the one we finally came up with was this rocking wall. It's got a soft joint at the base. It's got a shear lug at the bottom. And when the concrete carries the shear, the overturning goes into steel columns, which are spaced 10 feet on center all the way around the building. And then the overturning is transferred into the columns by this thing called, we now talk about it as the Krawwinkler fuse. Turns out just at the same time we were doing this, the Bloom Lab was in the process of testing a lot of these slit shear plates. And so I went out and had a couple built. It cost $20 a piece. Took them in the lab. They tested them, and the test worked out really well. And that's what we did with the building. We built it. We went to the contractor, Hathaway Dinwiddie, said, there's no way you're going to get this through the LA building department. It's going to take forever. I went to the LA building department with Helmut. We sat down. We explained to them all about how this behaved really well in the nonlinear region. And the guy said, well, can you design it in the linear region? Oh, well, yeah, we could. He said, well, just do that. Don't worry about it. And so, unfortunately, if you design all of these fuses to be linear at your MCE or at your design earthquake, it's really hard to get your strength down to where you want it so all the concrete survives. But anyway, that's what we did. We also, the high-def impart, we detailed all the rebar in the structural model so that they could prefabricate everything, and they ended up finishing this job in a fraction of the time that they had expected, and at a fraction of the cost. But when you have to do this, talking about a performance-based design, you're going to have a specified damage that you're going to be able to repair. Nothing else can be damaged. So if you're going to have a rotating wall on a four-story building, where it joins to the diaphragms, you have to accommodate rotation. So there were a lot of details associated with this particular project, and all of those details got built in. This one, you can see the rotator, that's the connection to the diaphragm. In our structural model, it's shown there, and then what it looks like in the field. This is our base connection. And there's Helmut inspecting the construction. If you look behind him, you can see all these plates sticking off the columns. Those are the shears. We fabricated them on the column, built the column first. Well, that meant we had no lateral system until after we put the walls in. If you look to the left of Helmut and John Ostras, there's some braces there. Temporary bracing all the way to the top of the building. It became a really simple sheer four-story steel building that could be erected in almost no time. Pour the slabs and start putting everything else in while we built the exterior walls. So it worked out really well. That's how it ended up at the finish. The next project was Isla Capri Casino in Cape Girardeau, Missouri, 2011, 2012. This project we did with rocking frames. Those, you see the 10-foot wide frames are all shop fabricated. They're all pre-stressed with DWDAG rods, high-strength DWDAG rods, so that they can rotate. The fuses in this case are actually the overturning. Once it starts to rock, the overturning goes up to the truss at the top, and the fuse is in the connection between the truss and the vertical member there. You can see the sort of details we came up with that. I put this one in here because I was out in the field inspecting this the day I got the word that Helmut had passed away. So this was his last project he did with us. That's what it looked like in the finish. And then we got to 2016. We were brought in on the Gigafactory, and no one was really interested in performance-based design. They were really interested in really, really fast. And so we did these DE, D prime, E prime, F buildings. It's about 350 million square feet. And we came up with a system of tied strongbacks, We had a couple different kind of strong backs. We had strong backs that actually rotated at the base that you're seeing in this on the bottom at this point. That formed a strong back that was fused. It was connected by crawling for fuses to a gravity column. So once it reached its design load, the fuses could yield all the way up. And then after that, we had BRBs that would take over and keep increasing the reaction. Up above, we had to interface with some existing BRBs, and then on those sides, we put in the same rocking strong back, but this time we just made sure that it was BRBs, not fuses at that point. Just to give you a size for scale. That's what the fuses, crawling for fuses look like. That's what the test looked like. It very well behaving. And let me see. I left one out. Anyway, anyway, I want to give a couple shout outs here now to other folks. David Marr has been doing a lot of work. These are just 6, 8 samples of his work on performance-based design. He's also got a strong back solution in there. Professor Jerry Hajar was part of that original research on the fuses. He's taken it further than that. In Northeastern, he's also now expanded performance-based design to include a lot of other things like sustainability, and that sort of thing. So I want to shout out to him, performance-based. Professor Convinde from UC Davis, I'm sorry. And this is a paper he had here last year, I think, or 2 years ago. And I was gratified by all the free body diagrams on this. They're beautiful. I mean, that's what Helmet was all about. We could not have a discussion about a performance-based design without a free body diagram. And I know Professor Convinde has done other work on fracture that is more substantial than this maybe, but I really like the free body diagrams. And then finally, Doug Hobach is out here somewhere. This is at Stanford. He did the new roof for the Stanford tennis courts. And this is actually using tension braces. And you can use tension braces as an ordinary braced frame in this category D. But he's also got a fuse in that the base of these columns, which the columns are designed to carry the full strength of the tension braces, but the base is designed to actually rock with D-Redag anchors into the foundations. And that's it. That's my little, oh, it's not it. I'm sorry. Insanity. So innovative design. Insanity is doing the same thing over and over again and expecting different results. These are my corollaries from a structural engineering point of view. If you want same results, do the same thing. If you want different results, do something different. That's obvious. But if you want to do something better, find out the best that's been done and do it better. That's the only way to be the best. And then my last slide is just tribute to Helmet. And I think Helmet was a mentor to all the current faculty at the Bloom Center, and he left us in good hands. Thank you.